This meeting is being recorded.
So our next reaction that we'll take a look is 8.11, is discussed in section 8.11, this anti-dihydroxylation. So as the name, again, kind of directs us, we know that we're adding two hydroxyl groups, right? The dihydroxylation. And we'll see that they add in an anti-fashion. So there's a two-step process that we'll walk through to go from our alkene to our dihydroxy product that results here. So first step, we have in this procedure, we have the formation of what's called an epoxide, which we'll talk about in a subsequent chapter. And our product that results in the second step is a transdiol. So we can see that the trans comes from the fact that one of the hydroxyl groups is on a dash and the other one is on a wedge. And of course, we'll see the enantiomer as well as a product. So let's take a look at these steps in more detail. So we have our cyclic alkene, or alkene rather, here. And we have what's called a peroxy acid. So there's a couple to note here. This is, instead of acetic acid, right, we have this extra kind of oxygen in there. So there's an oxygen per the acetic acid, so hence the peroxy acetic acid. And then over here we have meta, right? So this and this would be the two substituents on our benzene ring here. So one is the benzoic acid portion, the other one's a chloro. And we'll talk about this orientation in chapter 17 when we talk about aromatics. But when they're separated by one carbon, this is called meta here. So we have the benzoic acid portion, the chloro portion here, and then the peroxy with that extra oxygen here. So these peroxy acids, whether it's peroxyacetic or MCPBA, can be used to convert a cyclic alkene to what's called an epoxide. So that's the step one in our dihydroxylation process here. So we have this epoxide that was already formed. Then we have a proton transfer that occurs, right? So we have a hydronium here, right, H3O plus, and we protonate our epoxide. Water, right, in this next step, we have a nucleophilic attack. Water acts as a nucleophile. It attacks this protonated epoxide, and water adds to our ring down here. And then we form an enantiomer in this step, but the last step involves a subsequent proton transfer to deprotonate this oxonium, right? This is our oxonium ion that results here. We'll deprotonate that, and then we see this addition in the anti-fashion for two hydroxyl groups. So we call this anti-dihydroxylation. And of course, the product will always have its pair, its enantiomer. So there's a comparison here between, our intermediates for oxymercuration, demercuration, our halogenation with the bromonium ion, and then this protonated epoxide, right? So we see how all of these have a similar intermediate in the steps in the process, and all three yield anti-products. So that's good to know. So we will look at the counterpart to our anti-dihydroxylation in section 8.12 next time.